Hello everyone, I'm Holme from Tokyo Institute of Technology. I will teach this lecture in the online course Complex System Spectral Methods about temporal networks, which is one of my favorite research topics. I hope you all enjoy it, and I also thank the organizers for putting together this class, and thank you students for watching my lecture. So first I wanted to say a little bit about myself. So I have my PhD in physics, and these logos are like the universities of my career. Starting from when I was a student, I started out in Uppsala University in Sweden, in the top left. Continued studying Chinese in the Stockholm University and also in Fudan University in China. I came back to Stockholm University to finish my degree, and I also finished a degree in engineering or physics. Then I got my PhD from Umeå University. I spent the last year at Nordita in Copenhagen at that time. That's the star logo. Then I did my postdoc with Mark Newman in Michigan and Stephanie Forrest in New Mexico. I came back to Sweden, to KTH, Royal Institute of Technology, and then back to Umeå where I did my PhD. I also had a joint appointment with the Institute for Future Studies. Now we're on the third row, and then I moved to Korea. So the second last logo is the Sungkyunkwan University in Korea, and the last one, where I am now, is the Tokyo Institute of Technology. So my career has also been kind of going around to different places. My research interest, just as me in my life. That's kind of the take-home message from this slide. And if you want to know more or want to see my other presentations or my publications, you can check my homepage. Okay, so this lecture, I'm just going to say what I want to learn from this point. I know this is a class about, or the course is about spectral methods. And this lecture will not have many spectral methods. But I hope you can apply what you learned from the other lectures to temporal networks. Because temporal networks is a field that has a lot of low-hanging fruits and many open questions. And many questions that also can be solved by spectral methods. And it's not very hard to get started. I wanted to have that feeling after seeing my lecture. So it will be pretty basic, maybe more basic than other lectures, but I hope you enjoy it. And I also want to teach you, of course, the first point, that there are a lot of temporal structure that is important for many real-world phenomena, and we cannot ignore it. So let's get started. And I also wanted to start this slideshow a little bit slow, so I just want to give some kind of brief introduction to network science. It also applies to temporal networks, both static and temporal. So I'm sure many of you have seen this illustration. It's I think originally Indian or Thai Buddhist illustration, making a little bit different point. But my story to this picture of an elephant and a blind people examining it, so they see different things than an elephant, is that to understand like a complex big system, you have to step back and look from a distance. You cannot be too close. And like stepping back and looking from a distance, what that really means is to throw away details. And one way of throwing away details consistently is to represent the system as a network. But this is kind of where the analogy breaks down, but because you can't. Like representing an elephant as a network is maybe not such a good idea. But another system where it is a good idea is the interaction between people. So in this slide I want to kind of explain the kind of four-step procedure how to do network science. And the first thing, of course, you have to do is to observe your system and make a network of it. So in this case, assume that this is the network we get. Then you have to measure something. You can measure the number of triangles, and it should be 4, not 3. But just to test you. Okay. So you take your system and measure a network and measure something about the network, the number of triangles. But what does it mean? Okay, 4 triangles, like, so what? What does it really mean? This is when the network science comes in, because this is where we have to be able to interpret this number. It's like 4, is it a big or a small number? If it's a big number, then we can draw the conclusion that among the people we study, there is a tendency for triangles to form. And then kind of continue asking, like, why? Or we can kind of draw a conclusion not about the system, the network itself and how it formed, but about the like dynamic system on the network. So for example, like if you have many triangles, maybe rumors will spread more slowly. And then you can ask this kind of more like engineering question, like how can we improve this thing? So this was all for static network, like networks that don't move. What about temporal networks or dynamic networks? So this is the kind of cartoon you can have in your mind for what temporal networks really are. So let's follow this girl around her everyday life. So at different times of the day, she meets different people. So this kind of illustrates 2 aspects of human contacts. One is the temporal aspects, like when people meet, and then the other one is the network structure, the binary interaction. And there can be like structures or regularities in both time and the network that affects things, like how rumors spread or how disease spread. And the study of temporal networks is about understanding this connection between the structures in time and topology or network structure and the dynamics on the system, like opinion, information spreading, disease spreading, and so on. So yeah, now you meant, okay, so I took the triangles as an example of a network structure. Like, what is a good example of a temporal structure? So one thing you can do is that you go to your email outbox and then you make a timeline of when you send things. So not receive, but when you send things, when you send emails, and you can make this kind of timeline, like I did here. So I don't think this is email. I don't think I ever sent this many emails, but this is something I did for a popular science article in Swedish. So you can practice Tuesday, Wednesday, Thursday, Friday in Swedish here. But you can see, one thing you can see here is that these lines are not kind of randomly scattered around. There are some big gaps. It's like when I sleep, right? And then there are some kind of intense activities, a burst of activities. When that would be like when I have time to sit down and send my things. So this is called a bursty behavior. When you have this kind of long gaps and then intense burst of activity. And that's very common in many temporal networks. We'll talk more about that later, but now it's just an example of a temporal structure. And okay, so let's talk a little bit more about like how to understand network structure and function. And this, of course, applies for both temporal and static networks. We can call it the central dogma of network science, by analogy to biology. And the first thing, which I already alluded to, is that networks have some kind of structure. And the structure, what the definition of structure is that like this is the way a network differs from a random network. And like understanding the structure means that we can understand how the network formed. So how can we do this? If we go into details in this definition, this how part means that we need to measure quantities. We need to measure the number of triangles, for example. And we have to compare it to something. Because what is a random network? We have to compare it to the same quantity, the number of triangles, for example, in a null model, in a random model. And then from this we can learn something about how the system evolves, what are the kind of mechanisms that drives the evolution of the network, and also like how would dynamic systems such as like spreading phenomena or random walks and so on, how would they behave on the network. So this is, I call it central dogma 1 because it's about the entire system. Now we can zoom in and look at like nodes and individual nodes and links. So they have positions in the network. They are located at specific places, right? So position tells us something about where a node, how it is connected to the rest of the network. And to understand a position of a node or a link, we don't have to have a null model. We have to measure quantities, of course, but we can, instead of comparing to a null model, we can compare it to nodes and links in the rest of the network. So position is something that tells us about the nodes or links' role in the evolution of the system, and also like how the dynamic system on the network is affected by this node. So you can turn position metrics into some importance measure. What is an important node or link? Excuse me. So for network structure, we can measure typically the degree distribution, the density of triangles, community structure, that's kind of like finding dense groups in the network, and measuring network positions. Example of that would be the clustering coefficient, degree assortativity, centrality measures. And I think you heard about this in other lectures in the school, or otherwise it will be quick to find the references to learn about it. And of course the strength of network science in general is that it's just so wide. It applies to so many things. So just to show you some examples, this is what I used to do to kind of motivate network science for many people. Maybe you already know that it's important for you, so you can skip it. But anyway, like this is power grids. So power grids are like very tangible networks that are also, of course, very important, and we can also see them everywhere. You just go into the countryside and they are just there. A very good network. Another example is the social network. So this is a Norman Rockwell painting. It shows like a rumor going from the beginning to the end, and it kind of cycles back in the end, which is maybe not so representative. Especially this cycle is kind of like maybe too long. But anyway, it's an example both of an interesting network, the social network, and a dynamic process on the network. Okay, so here's my next example of application of network science. It's food web. It's a network of who eats whom among different species in the African savanna. And of course this is important, especially now when we're facing climate change and we want to maintain the biodiversity, to understand how this the structure of a food web affects the stability. And finally, and this is a little bit just to show just how wide the network can be applied. This is a picture, it's a sketch of a rock carvings in a cave in India, showing the different events in the life of an Indian prince. And the point of this is that a narrator can tell the story of the life of the prince by standing next to this grot, the rock carving, and pointing to the wall, and then different events that are related to each other are next to each other. So this is it's called a narrative network. So different events are connected by cause and causal relationships. just to show you. Of course, there are so many other types of networks: computer networks, networks in manufacturing, finance, biological networks, brain networks, even like you can even analyze games with networks. Everything exists, language and so on. Okay, so these are, most of these networks are probably just static, but many of them you can understand them as a temporal network too. And okay, let's be a little bit boring now. This has been kind of like the nice pictures and so on. When I get the temporal network to my computer, it almost always looks like this. So it's like a 3 by n matrix, basically, with like 3 columns, one showing the ID numbers of nodes and the third one showing the time. Each line represents an event, so it could be like an email being sent, or like 2 persons meeting at a time and something happening between 2 persons at one time. And of course this is kind of this is a good format for a computer to read, but it's kind of not a good format for humans to kind of reason about it. And I'll come back to that later. Let me just show you another type of format, another way of representing temporal networks, which would be especially appropriate for this class, because this is where you can talk about the spectral methods. So this is called like you know the adjacency matrix for a static network. So it's a matrix where the element ij is 0 if there is no link between I and j, and it's 1 if there is a link. In the temporal networks, we have the time is resolved, right? So you have to what's a matrix for static networks becomes a 3-dimensional tensor for temporal network. Well, yeah, I'm sure you can understand this. Then another type of temporal network, many times it's not, temporal network represents like 2 persons maybe meeting, discussing something, and they're leaving after a while. So the contact in the temporal network in that case is extended in time. So then you can represent the time of like duration of a contact, the beginning and the end, as an interval, as like 2 numbers. So this is called an interval graph. And here you might want to kind of like stop and think for a while, because I mean, even if you can kind of mathematically transform different representation to each other, and in fact all of these, I mean, you can more or less without any loss, kind of convert to one another. But it actually makes a little bit of a difference, and because it makes a difference in how you think about the network. So even this kind of very abstract representations, I can see from reading papers, for example, that people who are typically thinking of their temporal network as this kind of list of contacts, as we see here, or the interval graphs, or like a tensor, they get different ideas, and they kind of apply different methods. And of course it works in the other way around too. If you want to apply some specific methods, you should choose a representation that fits it. So this is a bit of a philosophical question, and there's kind of no clear answer. And I mean, I cannot even guide you, but it's good to be aware of this. Then okay, let's turn to graphical representations, because as humans, when we want to think of something, if we want to come up with a method to analyze temporal networks, we rather want to have some kind of graphical representation in mind. Just as we can draw like a network of people, we want to kind of draw a temporal network. And this shows a timeline representation. So here, every line is a person, and there's this vertical connection. If there is a contact at that particular time between these two persons. So this is a good representation if you want to see the structure in time. But you kind of lose the feeling for like how things are connected into the network topology. If you look at this, you can see that there is some kind of gap with no activity between time 11 and 16, but there is like high activity around 10. That's very kind of visually accessible, that information. But you can't count the triangles very easily. You have to kind of think a little bit before you can do that. So. And another graphical representation would be to make a similar timeline but of links, and just show the contacts at the link. Then you lose all the static network structure, but you get this feeling for the burstiness better. Or you can go in the other direction. You can just project all the contacts to a regular static network and kind of put the times of the contacts on the links. But then you lose the feeling for when things happen. So this is a bit of the dilemma, that there is no fantastic representation. Yeah, I also have to mention that there, of course, we also have this. We could make like a film clip, of course, like showing all the contacts as they evolve in time. But then we lose we don't see all the information at once. So in short, like the power of static networks is that we can draw the network and show it to just anybody, someone who is not interested in science whatsoever, and show how things spread around this network, and they'll understand it. And it's also great for us because we can just draw it and then see things spreading on the network and understand and kind of reason about networks in this way. But temporal network, it's not like that. It's much more it's more difficult to visualize it. So that's to some extent something we have to live with, but that much said, there might be better visualizations than the ones we've seen. Okay, so like now we have the basics. We understand what the temporal network is, the mathematical representations. Now we want to study the world, right? So what kind of empirical temporal networks are there around? So one type of network people have been really interested in studying is this proximity networks. Basically, like when two persons are close to each other. So in a normal lecture, I would point at you and say that, okay, we're all in this room together and like we're all kind of close to each other. This would be recorded in a proximity network. Now it's an online lecture, so we're not. So we're all isolated. But anyway, so people have been really ingenious to record these different types of proximity networks and used many different types of tools to do that. This RFID tags is maybe the most successful and most common one. So this is my conference tag from a conference a few years ago. So you can see this little chip. It is a RFID sensor that records when I'm close to another person with a chip like this within 1.5 meter, roughly 1.5 meter distance. So okay, so this is a illustration of like how people move around for another conference. This is not the conference where I was, but this is once again kind of showing the kind of complexity of this type of data when you get it. It also shows like, okay, like you can kind of pause this video and see the kind of static network structure. But if you see a film like this, you can't really kind of like reason because you don't see everything at once. So you don't really have a feeling for if everybody meets everybody, or yeah, so many things. Just saying that once again, there's no like perfect visualization. And now I'm just going to continue. So on the previous slide I showed you many different ways of measuring proximity networks. There are also human interaction networks where we, like me and you, the audience, could be connected because we are kind of all participating in this online class. And then, of course, electronic communication, I already mentioned, emails and social media messages and so on. And people have been interested in temporal networks applied to transportation networks, like air travel, also neuroscience, both at the kind of neuronal level and brain level. In ecology and population biology, they are not so well studied. I think this is like a potentially low-hanging fruit for applications. There are animal social networks about zebras, monkeys, and ants and so on. So the ants are typically measured by a camera, and when they stop and interact, there is some kind of video processing software that identifies this contact. While in the like larger animals, when they have this kind of GPS tracker, and when the kind of one animal, or the kind of GPS location of two animals overlap, you can call that a contact. And people study the economic networks by like credit card transaction, loans, and so on by the temporal network. In biology, there are many temporal network systems that could be modeled as temporal network, like gene regulation, protein interaction, and so on. But also the quality of the data has not been so good so far. But of course, they do improve all the time. So I think that this is another area of application that we should keep in mind. Okay, so before I talked about this kind of lossless representation, where all representations that have everything in the network. Of course, we can kind of like project a temporal network to a static network, because of course, static networks, we have so much more tools to study them, right? So one way and the kind of most common way of doing it is to use something called a reachability graph. So in this network, it's not like every node can reach each other. So if you think of this as a static network and you remove all the timestamps on the edges, then of course you can go from one node to another through the network, right? So all the nodes are indirectly connected. But this is not true if you think of it as a temporal network, because there is no way of going from A to E or from E to A. There is no way of going from A to D, but you could go from D to A in the previous picture. So this is called a reachability graph, where one directed edge means that you can go from one node to another following this we call it a time respecting path, so following like an increasing sequence of contacts, because if you kind of traverse or travel in a temporal network, you cannot go backward in time, right, in the most practical applications. And this shows another type of way of kind of reducing a static network to a temporal network. This is kind of keeping all the information, but it is kind of destroying the meaning of a node. So instead of one node, you replace it by a node at a given time. And we can think of this in many different ways, but like if you think about conferences, and conferences would be kind of connected by the participants. If two conferences have a common participants, then they are connected. Then in like all the other representations, say like a conference like NetSci, which is the biggest network science conference, would be like one node. But in a time node prediction network, it will be like NetSci 2017, NetSci 2018, NetSci 2019, and so on. That would be a node. So a node is kind of like an object at a given time. And another way of making static network is to make time slices of the network. So you connect the nodes that are have a contact within some kind of time window. And the network structure itself is very sensitive to the size of the network. So this is from a paper by the Sune Lehmann's group. They show that as you decrease the time window size, the network kind of starts breaking down. And here we can stop and think for a while. Like, so what does it mean? Even in this representation, the network being kind of fragmented, it's still meaningful. This means that people are together, maybe in a room, in a classroom, or in a car, or in a bus, or something. But this is for a temporal network. It makes sense to have a fragmented network, but in a static network, it doesn't make sense. And yeah, so this is one thing we can think about. There's kind of fundamental difference between temporal and static networks. And we can also think about like what we like to talk about timescales in complex system research. Like, what does this mean with respect to timescale? And like, how can we use this type of fragmentation to kind of characterize the timescales of a network? And there is kind of, I will talk a bit more about this later. At the end of this talk, I hope to present some of my own projects. But yeah, this is a kind of open question. And just as in static network, it's important to the concept of path and shortest path is also important for static network. But also this becomes a different thing. So I already told you that the time-respecting path is a path that doesn't go back in time. So it's very clearly visible in this type of timeline graph, because it's kind of a line that doesn't kind of go back in time. Important metrics for characterizing paths is called latency, and this comes from the computer science literature. Leslie Lamport, actually the inventor of the LaTeX typesetting system, he was the first to discuss this. So latency is the duration of the shortest time-respecting path from I to j starting at a specific time. So essentially, whenever you generalize something from static networks, this will become time dependent in a static network, in a temporal network. Also a simple concept as a path. Then of course you can kind of average out the time and so on. But to start with, of course you shouldn't do that. And latency typically have this kind of like a sawtooth pattern, where it kind of, whenever there is a contact, the latency goes up. It's like you miss the bus, so you have to wait longer. Another important concept is reachability. And there are a few different definitions around in the literature. One is the fraction of vertex pairs at a certain time that are connected by a time-respecting path. But in general, reachability tells us how large a fraction of the network is connected at a given time. Another thing is called burstiness. So this is something I also mentioned before with my emails. So people have this kind of like bursty behavior. This is data from a prostitution, from an online community of sex buyers that evaluate their experience with prostitutes or escorts, and so the lines at the where it says escort, it shows when this escort is active. So this itself has a bursty behavior, and the sex buyer, these lines shows when he has bought sex, and that is also bursty. It also has this kind of gap and like intense periods. And then the lines that goes through both are the ones between this particular escort and this particular sex buyer. And so it's kind of link property, which is also bursty. And then burstiness is something that we typically measure by this Fano factor, or coefficient of variation of the time between events. It's from this paper by Go and Barabasi, you can see in the lower side of the screen. Another measure that is very kind of important, or a structure that is important, is the persistent pattern. So like, so many types of temporal networks. So you can think of these proximity networks where people are close together. Like the probability that you will be close together kind of in the next time step is high. If you've been together at time 1, then probably you will be together at time 2 as well. And this could be measured by this adjacency correlation function by Aaron Closet and Nathan Eagle. Or you can in principle think of many other way of measuring it, but the important thing is the idea that a very strong effect in temporal network is this autocorrelation, that if two things are connected at one time, they will be connected soon after too. And this, as I already said, like all this concept generalized from statical network, they will be time dependent, including ideas as like components, strongly and weakly connected components, and all other types of static network measures. So how to predict the out time it's not the kind of like easy thing to do. I recommend you to look in the literature or kind of think for yourself. I think there are always many ways of doing things, but there might not be like one definitely best way of doing it. So in many cases in my projects, I reach this point and what should I do? How should I proceed? And in the end, you just end up trying to do the simplest thing you can come up with. But even what's the simplest thing is sometimes not clear. And this is true for like centrality measures too. So I think all of the classical centrality measures, betweenness, eigenvector centrality, closeness centrality, they can be generalized to temporal networks. But they will typically by replacing distance by latency. But they will measure a little bit different things. Okay, so here we can also kind of stop and think for a while, because in many problems for static networks, this kind of size scaling is important, taking the n goes to infinity limit. This is not straightforward at all for temporal network. In fact, there is almost no good way of doing it. I mean, because if you rescale the duration of a temporal network, then you also would have to rescale the number of nodes. Because, yes, say you kind of like, you sample a group of people for 1 day, and you think of a spreading phenomena. Then you kind of scale up in your simulation this data set to 10 days. Then maybe the spreading phenomena can spread to everybody, while originally it couldn't do it. So that means you change kind of very fundamental property. You kind of destroyed one structure, one feature of the original data set that you rather want to keep. And yeah, so that also means that kind of rescaling, sizing up, scaling up and down temporal networks is actually something that you should do kind of with respect to a dynamic system, and like how to take this into account. These are things that are completely unknown, and I welcome you all to kind of both kind of contribute to the temporal network science and solve this problem. How can you deal with this kind of thing and bring this finite size scaling framework that is very powerful for static network into temporal networks? Or at least you should kind of like keep this in mind, that it's not an easy thing to kind of like resample or change the size of a temporal network. Now let me say a little bit about like coding and software. And I mean, there is no kind of like standalone app that you can download to analyze temporal network. There are, say, Gephi, that's pretty good for static network. It also has some kind of temporal network functionality, so I can recommend that. But if you want to kind of contribute to the science, you would have to code for yourself and use some kind of general language. I myself use Python or C. I think you can use R, MATLAB, or other ones as well. And there are some temporal network packages for Python, for example, but it's not as complete as for static networks. And typically the file format would be this kind of contact sequences, and sometimes interval graphs. So it's not true. I have seen interval graphs, but 99% are contact sequences. And like in your code, you can typically use contact sequences as well, or like a linked list with contacts on the list link, or a adjacency list. This typical structure for static networks with the kind of like another list of all the contacts per link. Or you can have this kind of adjacent tensors, as I mentioned, if you're studying spectral properties. Or as this kind of screenshot shows, and this is C, I think, or I know, it's the breaks it down the data into each time step. So each time step stores the number of contacts, this particular time step, and then the nodes that are connected. These are, in my case, I store it as arrays of unsigned ints. And yeah. And okay, so this is another time to stop and think for a while. When you write the code, this is something, a point where every temporal network person will have to stop and think. Because say there are two contacts at the same time between A and B and C. And then typically you're studying some kind of spreading phenomenon, maybe like a disease spreading. In this situation, can things spread from A to C via B or not? I mean, there is no like kind of general answer to this. You have to kind of think of the dynamic system. If it's a disease spreading, is it possible that during one time step, one person B can kind of get infected and then transfer the disease to person C? Okay. And yeah, the responses in your code would be different. So if one thing you can do is that you allow for the spreading, but then you have to think about what happens really within one time step. Then if you want to be principled, you have to kind of repeat whatever you're doing with the contacts coming in random orders, and then take average over this many randomizations. Yeah. Okay, so for dynamic processes, just as for static networks, in temporal networks we're interested in something spreading on top of a network. Usually the interesting thing is like a one-to-many interaction, like spreading of disease spreading, modeled by simple contagion models like SIR, SIS, and so on, or opinion spreading models, rumor spreading, and this could be like modeled by, say, threshold models or so on. a little bit less interesting, because like just what is the application here is random walks. So like of course random walks are very fundamental, and you can use them to probe a temporal network. But there are not so many systems in reality that I can think of that are well modeled by a random walk on a temporal network. And then, of course, there are other things too, like synchronization problems, game theory, and so on you can study. So this is similar to static networks. There is a rich number of kind of rich set of dynamical systems that you can study on a temporal network. And the most common one to study is epidemics. So just to introduce you a little bit to modeling epidemic spreading of infectious disease, then I have some cartoons for you. So in this picture on the left, we see a person that has the disease, an infectious person, and a person that can get the disease, susceptible, having a contact. So this is, once again, in temporal network, is like one row in this list of contacts. Two persons having contact, and then after some time, then the susceptible will become infectious. And then after a while, the infectious will of course become recovered. So this kind of defines the two fundamental epidemic models: the susceptible infectious susceptible and susceptible infectious recovered models. One for diseases that you become immune to after you're recovered, and one for the ones where you get resusceptible. And typically these steps are modeled by either transmission probability, per contact transmission probability. That's the most appropriate for temporal network studies, right? And the second step is that you would become susceptible or recovered after some fixed amount of time, or more commonly with this kind of some time chance per time unit, which gives an exponentially distributed infectious period. This is the common way of doing it in mathematical epidemiology. And so, but of course we also need this kind of like population structure. So this SIS, SIR, they just kind of show the different types of states with respect to the disease, and like how you can transfer between them. But there is also the social component, and this is where a temporal network comes in. And yeah, then if you check my blog post, I have some on my blog. I have some blog post about how to model disease spreading on temporal networks properly. And one thing that's not very easy or straightforward how to do is like how to choose the seed of an infection in a temporal network dataset. I mean, if you don't know anything, then you should choose something with as random as possible. That's the usual principle. But that might mean that you choose someone who is just present in the very end of the dataset. And then, of course, a disease cannot spread to many people, which you can argue is not so representative. But on the other hand, that's the most principled way to do, and that's the way I usually do too. But yeah, this is something to think about. Like, and there's no like crystal clear answer to how to choose someone to infect. So typically what I do is that I start an outbreak at one node, and then I pick a source node uniformly at random, and I also pick a time between the beginning and the end of the dataset at random to start the disease. And then if two nodes are in contact at one time, I don't let the disease spread through two contacts. and otherwise infection probability and is the same for all contacts, and I let the infection go for an exponentially distributed time to kind of conform to the literature. And then, okay, algorithms, that's something I also have a post on my blog if you want to check. But essentially it's extremely easy to make a straightforward algorithm. You just run through the contact list and just run the SIR states on this. But you can make something much faster. And yeah, once again, this is something you can check my blog, and I also have code on GitHub for making something called what's it called? Event-driven modeling of temporal network disease spreading on temporal networks. So I'm not going to go so much into details. You can check my GitHub page, or I have, or there is also this book, Mathematics of Epidemics on Networks, with also Python code, not for temporal networks, but anyway. Okay, so now I talked a bit about what is temporal networks, what are the different types of temporal networks out there, how to study them, what kind of software to use. Next I will talk a bit about my own research, and I realize I should cut this slideshow short a bit because time is ticking. But so when the first thing I was interested in when I came to this subject, this was kind of my last year as a PhD student, my first year as a postdoc. I made my first temporal network paper around 2005. Excuse me. Okay, so first thing I want to argue that, of course, I told you in the beginning that network representation is a good way of making complicated system simple. Now, of course, if we add time and kind of contradict that, so you have to get something out of making your network, your representation more complicated. Okay, so the first thing I already told you, that temporal networks are not transitive. In this network you can go from A to B, you can go from B to D, but you cannot go from A to D, because you can reach B by the time 11, and then all contacts between B and D already happen. But you can continue to C by time 17, but then all contacts between C and D already happen. So there is no connection from A to D. So, all static networks are transitive, right? Even directed networks. This means that this kind of hints that temporal networks is something fundamentally different, and that kind of I get that confirmed all the time. So my first study of spreading process was based on our study of this prostitution data that I already mentioned. So it's I also mentioned kind of how it works. So this is like how disease spreads in the worst case scenario on this network. And I think the slide is cut there, but it's a time on the x-axis. And we can see that this is spreading, taking off slowly and then spreading roughly linearly. And we wanted in a follow-up study to see like how does the order of event affect how things happen. And so what we do is that we take this list of contacts and then we just kind of randomize the timestamps of things and see how, in our case, then things spread slower in the randomized network, meaning that there's something in the data that kind of speeds up the disease spreading. So this is kind of funny because the week after we put this paper on arXiv, I went to a conference and met this Finnish guy, Jari Sarmäki, and we started chatting and realized that we put we did exactly the same analysis And they scooped us, right? You can see they were 4 days ahead of us with this result. But we used the sexual encounters in the prostitution data. They used the cell phone data. And they found the opposite thing. So in the cell phone data, then the spreading becomes kind of slowed down by the order of event. And before I continue, I should just say, okay, these curves are very close to each other in the previous slide, but so this is some much more modern data, and now it's a kind of so this shows the difference between the outbreak size predicted in a static and a real temporal network and a temporal network that is kind of randomized by swapping the contacts in the same way as before. And you can see for some data set the difference is like 60%. So this is huge. The time and the order of events can make a really big difference. But okay, back to this my encounter with Jari Sarmäki. So we couldn't really figure out why they saw a slowed down effect and we saw a speed up effect. But we agreed to write a review paper. So this is kind of like, by then I knew that temporal networks would be kind of a main research theme in the years to come. We also were editors of a book. We have another follow-up volume to this one coming up. So it was good for my career, even though the Finnish group scooped us. Okay, so one thing the Finnish group did was they did better than us, is that they didn't only kind of shuffle the time and look at the response. They made a lot of other randomizations. So this kind of so by kind of gradually destroying the structure of the order of events, that by swapping the timestamps, you can do that, but then you don't destroy the kind of like average activity over the day. So for example, at night there is less activity than during the day. That you can destroy by kind of reassigning the timestamp from a uniform distribution, for example. And you can also go in the other way and kind of keep more of the original structure in your randomization. So you can use this kind of randomization technique to show exactly what you want to keep in your original data to reproduce what you see in the original data. So randomization techniques in static networks is pretty limited. You can basically just sample the configuration model by doing it, but in temporal network it's much richer. And so that's another example for like how different temporal network and static networks are. So yeah, this is just showing how you can destroy the time, how you can how you can destroy the order of events. This is how you can destroy the time, that you replace the timestamps by random numbers. And then you can of course shuffle entire contacts of a link, and you can like that, and you can also restrict yourself to like links with the same weight, and this is like kind of keeping more of the original structure. So then in static networks, typically you kind of we take the empirical network and find like what kind of model network that can reproduce them, and we study the model networks. In temporal networks, I mean, there is an argument. I mean, you have to make the choice is not that easy. I mean, I always actually keep studying empirical networks just because it's very difficult to make a network model that keeps all the possible structure. Okay. Now let me kind of go a little bit faster. I think you can pause the slide and kind of read if you're interested. But okay, so motifs like small overrepresented subgraphs is something people are interested in the static network, and there some part of the temporal network literature also study that. I think you can just search temporal network motif and you will find the important citation. And as I mentioned, like models that generate the temporal network is also like difficult. It's difficult because we don't even have a clear view of like what are the important structures in temporal network. Even though this field has been going for like 5-10 years, people are still not completely sure how to do it. So, but still there are this model-based study. There is a famous model called the, well, I forget, but by Nicola Perra et al. Activity-driven model. Okay, now you got it. Okay, and here's another kind of counterpart of the configuration model for static network, that you can construct the temporal network by first kind of drawing degrees, then you connect them to a static network. Then you kind of create the kind of intervals when each edge is active. You generate some kind of time series, maybe with a bursty pattern, and then you kind of wrap this time series onto these intervals, and then delete the intervals, and voila, you have a temporal network. And in the previous slide I have the reference for that. But this is yet another time we can stop and think for a while, because in a temporal network, what is a contact is sometimes kind of like an effect of the process that we want to study. So it's like how to model a temporal network. Yeah, for many reasons, both because we don't know all the structures, and then also like what the kind of contact actually means. So typically if we want to study kind of information spreading, and we take the data from an email network and kind of model some kind of spreading process by a SIR model on top of this. I don't know if it makes sense, but we could do it. But then the question is like, I mean, don't you use emails to spread what you want to, the information you want to spread? It's not that the information you want to write an email to someone and then you just put all the information you have there. So just from a fundamental modeling point of view, you have to be aware that say the links in a static network and the contacts of a temporal network are not really one-to-one mapping between them. Okay, so in static networks we have this fat tail intervent time distribution. There was this idea that kind of slows down spreading. That explains this Finnish group's finding of for the cell phone data, but the fact is that this in our prostitution data it also has fat tail intervent times, but now that kind of something speeds up the disease spreading. And what is it? So there was actually many studies that kind of just assume that this kind of burst intervent time distribution is the most important thing, most important temporal structure, and let's just study that. But it's not the case. It's not a so interesting direction to go. So what could it be that is more important, at least for like disease spreading? Well, I mean, there could be this beginning of a relationship and then an end of a relationship. This is actually a very clear structure in many of the empirical data sets, that people interact with each other has a very clear beginning and end. So this was this was maybe my first temporal network paper as a PhD student back in 2003. But other people made the same observation. So in a study, the that we published, now it's maybe like 5 years ago or even more. We can contrast two pictures of simplifying a temporal network. One is, we call it the ongoing link picture, assuming that whatever you see a contact, it's sampled from a link in a static network that was there before and will be there after the data. Contrast that with another type of dataset, which is like a link turnover picture, which is more like this kind of beginning and end of relationship, that the relationship starts at some point and ends at some point. And we argue that this second one is the most important one, and we do it by some randomization type model. Actually, in this case, we didn't have computer power to do full randomization, so instead we destroyed it by making everything equal, or destroying this so the first one destroys the inter-event time structure, the second one destroys the where we kind of shift all the contacts to the beginning. It destroys this kind of link turnover picture, or we could shift it to the end too. And then we measure the SIR model outbreak size. So as in temporal networks, the SIR model has two parameter values determining the probability of getting disease transferred and the duration of the disease. And what happens if we kind of destroy the inter-event time, the burstiness? Well, this happens, almost nothing at all. But if we destroy the beginning time, then something more happens. And if we destroy the end times, something more happens. So, but I mean, this together with some other argument made us think that this kind of turnover of links is something very important. That when the links start and end is much more important than the kind of the time in between. So this plot shows like different data sets. So this paper is a few years old. Nowadays, my collection of temporal networks is maybe 150 different data sets, but here I had much fewer. Okay. Then let me flip this one pretty fast. So this is a study I made, like how to kind of project a temporal network to a static network so that it retains as much information as possible with respect to disease spreading. That's at least an example of an interesting question that I encourage you to study. And also, I would make this a lot different. Today I learned to, in this case I didn't scan the entire parameter space. I used a Spearman correlation coefficient that is not appropriate for this. I still think the conclusions are probably true, but I learned a lot since this time. So now I'm just showing you some of my own projects to give you some idea of what people can do. Another thing I was interested in is R0, the basic reproduction number, which is a very important concept in mathematical epidemiology. Much because it is one of the few concepts that went from mathematical epidemiology to medical epidemiology. And even Hollywood knows about it. So this is Kate Winslet writing R0 and a screenshot from this film Contagion. So R0 is basically a quantity that shows how serious a disease is. And for medical people on the mass media too, they use R0 just as representing how serious a disease is for a population in general. So here you can see some examples of R0, and you see the childhood diseases, they have the highest R0. So essentially when they come to a susceptible population, they just kind of burn out in the population, and they have to wait until there are new people susceptible born and grow up before a new wave can spread. But okay, so the R0, this quantity measuring like how serious a disease is, comes from this original differential equation formulation of the SIR model, where R0 is the ratio between the infection rate and the recovery rate. And disease can spread in the network if and only if R0 is larger than 1. This defines an epidemic threshold. But there are lots of problems. It's hard to estimate. Threshold isn't 1 in practice. What does it mean with a threshold in a finite population? But also in a temporal network, the outbreak size doesn't even have to be a monotonous function of R0. So in this paper, we used empirical contact data and simulate the full parameter space of the SR model. We plot the outbreak size versus R0 and try to find out what kind of temporal network structure that creates the deviations. Okay, now something is a bit strange with this slide. But okay, this slide is for one data set, and every point is one point in the parameter space of the SIR. And if this R0 is a perfect predictor of the average outbreak size, which is something that people implicitly assume, then this would all fall on one curve. But you see there is a spread. So this paper is about what are the temporal network structures that creates this spread. So what we do is that we characterize the shape of this banana shape of the points as like a, so this kind of characterize how R0 fails to predict the outbreak size. And then we measure many different network structures about the temporal network structures, both the kind of topology and the kind of like link activity, interevent times, and also the evolution. If the activity in the network is big in the beginning and small in the end, or vice versa, or if it's constant, yeah, so things like that. And then we run kind of just a standard regression analysis to find what type of temporal network structures that are important for the shape of this banana, basically. So the width of the banana is depends a lot on the this kind of turnover of links and this kind of slow temporal network structures. The only thing that where the static network structure matters is this kind of the spread in the vertical axis. And yeah, please read more about it. Another interesting problem is the vaccination problem. So usually it's formulated like this, that assume that we can vaccinate a fraction f of a population. And how can we pick these people to vaccinate using only the kind of local information, so only by interviewing people? And I recommend you to try this app to understand this better. Now, in a static network, this vaccination problem was got a very nice solution by this Israeli group, Cohen, Havlin, and Ben Avraham in 2002. It's called the neighborhood vaccination, and it goes like this: that we pick a person at random, then we ask the person to name a friend, and then we vaccinate the friend, not the person we called. And this is a good idea because the probability of picking someone with a high degree is proportional to the degree. So it's higher for node with high degree, so it's a high chance that we find like a hub in the network to vaccinate. So we had a kind of study where we kind of try to adapt this neighborhood vaccination to temporal network. And now we can make it more realistic because we don't have to assume that the network doesn't change in time. We can use the past to predict the future. So essentially what we do is that we take a temporal network, break it in half, and then use the first as an experience period. Then at the midpoint we assume everything happens. The disease starts, the vaccination happens, and then we simulate the disease spreading and the vaccination in the second half of the data. And so this is one example how the disease eventually spreads to everybody. So we try different kind of versions of this neighborhood vaccination. We pick, and two of them works well. So we pick a person at random, and then we ask the person to name the most recent contact and vaccinate that one. And in this case it saved one person. And then we can pick a person at random and ask the person to name the most frequent throughout the experience period and vaccinate that one. And in this case, it saved 3. And in our paper, this is the kind of success plot in this paper. So it shows the outbreak size, how it was decreased. So whenever there are points in the yellow region, that's when our method were more successful than neighborhood vaccination. So we can see the fact that there are points in yellow everywhere means that there is always a temporal network structure to exploit, or temporal structure to exploit. But also different datasets respond in different ways. So this email data is different. And the reason, which took a while to understand, is that in the email data is special in that sense that the people that are there in the beginning, and links that are there in the beginning, they are there in the end too. So there is no turnover of links and events. Now this is a very old study, so people have done it better. And I think in this paper, maybe not, but I think they do use some kind of spectral method, kind of connecting better to this class than the one I used. Okay, so we're reaching towards the end of this talk. So one thing I want to say more is like what are interesting future directions. So one thing is like how to kind of properly model the contact patterns as temporal networks. What are the structures there? Then we need better visualization. And then, of course, we have so many results for static networks. We want to know how can we adjust them to take temporal effects into account. And as I mentioned, how to talk about timescales in temporal networks are actually not... People do that, but there is no kind of theory for it, no good theory. And then community detection, something I haven't mentioned at all, but this is also where people use spectral methods or non-negative tensor factorization. Once again, the philosophical question: what is a temporal community? Surely, like, I mean, if you want it to mean something, people that are kind of close to each other at the same time in a group, something like this, then it should also. It makes no sense to kind of split the entire population into communities. It makes even less sense than in a static network. So a fundamentally different thing, community detection in temporal networks. Also how to design fast algorithms and analytically tractable models. And we do know from a randomization study that time matters, but like how and like what kind of temporal structure or combination of temporal and topological structures that are the most important ones, we don't know. And if you want to read more, then I do have a few review papers. I recommend the latest one, the top one. And there is a book by Naoki Masuda, who also lectures in this online course, and Renaud Lambiot, that is a bit more technical than my review papers. So I think for you this is a better choice than my review papers. And the temporal network specialized epidemiology, Naoki Masuda and I have an edited book volume on Springer. And if you want to hear more about community detection, I mentioned this review paper is very good. In particular because I know many people are interested in community detection. I didn't have any slides prepared for this talk about it, so please check out this review by Rossetti and Kasper. Okay, with that I have to say thank you, and it's been an interesting experience to record this video lecture, and I want to thank all my collaborators too. Naoki Masuda, Yari Sarameki, Frederick Liljeros, Luis Rocha, Sungmin Lee, Fariba Karimi, Juan Perotti, Taro Takaguchi, Taoli Yuanbai, and illustrations by Mijin Lee. So thank you very much. Bye bye.